Welcome to homework.
Hi, everybody. So, determine the range of values of your frequency for which the amplitude of vibration of the block exceeds 3.5. Okay. And let me just draw this. And what you're going to do is exactly what it said. You're just going to find the frequency. Okay. I mean, there's no really better explanation than what the problem actually says. And you're using mechanics. Okay. If you don't know what this book is about. The book's about mechanical physics, okay? So you should know that. And there's not much to say else besides we're going to just follow along here with me because otherwise there's no point in sitting there detailing what I'm doing because I am telling you what I'm doing every step of the way, okay? We got B. And I'm just kind of copying, oops, just up to here. There we go. Okay. I'm just copying the figure, by the way, if you're curious what I'm doing. And this, what I'm doing is just copying the figure. I'm not doing anything special here. Okay, so in figure one, the angular displacement given in rod BC is the angle. And the angular acceleration of the block of A is the double integral of theta. So what we have to do is take the moment about B, okay? So take the moment about B. So right here, you see this B here, we have to take the moment about it. So looks like the force is going up. So you're just going to have to do the right hand rule, okay? And let's see, let's write this down for everybody. So we have the mass of B equals, so we have to do clockwise, okay? So we're going to do the right hand rule. So we're going to do a little handy motion and it's going to go clockwise, okay? Times B. Remember that this right here is equal to the A block, okay? And I'm just going to delete it because I want you guys to be able to see. So you see this NB, okay? And it goes about this B here. You see here how it's making a little triangle? Okay. And I'm going to put clockwise so that way you guys know what direction it is. Plus, and we have the spring constant times the L times the theta, which is this guy right here, times cross body product. Can you guess which what is? It's of this L here. Again, it's making a little triangle clockwise. Okay. And now we have the P here and the L. Okay. And we're just going to put CW clockwise. Okay. So if we do the cross body product for each one, we get m b squared theta plus the k l squared theta minus pl. Okay. So at equilibrium, the sum of the moment about B is 0. Thus equates MB is going to be 0 when it's at equilibrium. Okay. So we're going to set this whole thing to 0. And what we can get is actually mb squared dot dot plus kl squared theta equals pm. And what we're going to do is substitute pm sine, and we'll put this L here, sine omega t, okay, and for the p. And this is a periodic force. So pm is a periodic force. okay? And the WF is the periodic force and the time is T. So now we have to do the expression in terms of standard differential equation as m equals mb squared, k equals kl squared, and pm equals pml, okay? And so we have to express the natural circle frequency of the vibration for the standard differential equation as here equals km. And if we substitute these guys in here, you just realize I'm writing in red, but we're just going to keep going at it. And I apologize, I just kept writing in red. KL squared, MB squared, okay? So here the natural frequency of vibration is WN, and we can plug in our units that we have. So 2KNM, 800 mm, 20 kilograms times 200 mm, okay? And we're just going to convert these mm's to meters, so 10.3, and that's going to be 0.8 squared divided by 20 times 0.2 squared, and here we have 40 radians per second. So now we've expressed the amplitude of the motion in terms of linear displacement. Okay, and here we can substitute 3.5 mm into 200 mm, 0.0175 radians. So the amplitude of the vibration of the range is 0.0175. Okay, that's plus or minus. Okay, so now what we can do is take the vibration and express this vibration now as PM L MB squared over WN squared minus WF squared. Okay, and now we can solve for this guy here. So here we're going to do 0.0175. And it's going to be negative because the amplitude vibration is the range of negative radians to positive. So we're going to do it to the negative first. Equals radians equals 6 newtons times 0.8 meters divided by, and we're just going to put this all in brackets, 20 kilograms. And this whole thing is going to be brackets as well. Kilograms times 0.2 meters squared over 40, oops, if I can write 40 radians per second squared minus, there we go. And now we'll have 0.0175 radians equals 6 over 1,600 minus, there we go, frequency. And now we're just gonna keep solving. And we get 1,600 plus 342.857. And we're just going to take the square root, equals 44.1 radians per second. And now we're going to do, so we're going to put that off here. So now we're going to do the positive side, so 0.0175. And This side is actually going to be the exact same, okay? But it's going to be slightly different. I'm just not going to write all the numbers out because we don't need to. Okay, so from this, what's going to change is actually this is going to come out 1,600 minus 342.857 square root, and we get 35.5 radians per second. So what we have is 35.5, and let me write this a tad bit nicer. So we have 35.5 radians per second is going to be less than this frequency here, but that frequency is going to be less than the 44.1 radians per second. Okay, thank you.